That's loud. All right. Today we're going to talk about, well, the next two sections, section 283, deal with testing hypotheses with different part. This one in 8.2, we deal with population proportions, and in 8.3, we deal with the mean. It strongly depends on whether you have the population or the sample information because of accuracy and helps in requirements of what's needed. Of course, as always, we're going to look at the three methods to solve these: p-value, critical value, and confidence intervals. All right. First thing, finding the number of successes. You must have the sample size. That's n. The number of successes, whatever you define as success, that is what we define as X. The sample proportion, which we call P hat. Well, if you have the population proportion, it's great, but I'm not going to give up. So this is our X value. Because remember, for the probability of X, we're looking at what is the probability of success. And since that's the proportion what we're looking for, we're defining our success there. Normal approximation. Method. Remember, whenever you see the word normal, what does that refer to? And what does that look like? Bell curve, right? So whenever we talk about normal approximation methods, it's one of the conditions we have to have is it's got to be normal, it's got to be bell shaped. So we're going to use procedures based on normal distribution as our approximation. For binomial distributions. Why are they binomial distributions? What does that refer to? What is a binomial distribution? What does it look like? What are the outcomes? Yeah, only two possibilities. Yes, no, on, off, good, bad, pass, fail, win, lose. So those we're going to get. So that's what we're looking at. Because remember that's where we have the P and Q. Um, Notation we're going to use in this section. The P represents the population proportion. And when we do hypothesis testing, we're going to see that's what we're going to be using. Whenever we do hypothesis test, hypothesis will be P is less than 2 or P is greater than equal to 2. All right, so in this case, that's what we'll be using. Then we'll also be using P hat, which is the population. I mean, that's a sample portion. That's our approximation. And we'll have a couple of formulas we'll be defining for this one later on. So that's the formula we'll be using for it. Where N represents the sample size and Q represents the 1 minus P, the other part of the binomial. If P is success, then Q is a failure. Requirements. In order to reuse this process, we have to have certain conditions that have to be met. The simple random, the sample has to be created by a simple random sample for your observations, your data collections, or whatever you're doing. Samples must be binomial, which leads us to a binomial distribution. Now, for binomial distribution, we have some conditions. Has to be finite, fixed number of trials. Each trial is independent of all the other. What does independent mean? Oh, that's using my way too. I hate it. Using my way also hate it. What does it mean by independent? Very good. Very good. It's exactly that's out of the textbook. Yes, the results of one event doesn't affect the results of the other. Each trial has only two outcomes possible. And the probability of success is the same for each trial. Those are the conditions just to be binomial distribution. And pretty much common sense, really. If it's binomial, then it only has to have two possibilities. That means your outcome is going to be two. And they have to be independent, because if one affects the other, then you can't determine what's going to happen in the future. Okay, so back to the original list. Number 3. The conditions n times p greater than or equal to 5 and n times q is greater than or equal to 5 must hold. And for the, what does the row stand for? Of the, it's Greek, so is it sample or population? Population. So is standard deviation of the population. And that only works for binomial distributions. Right. So let's look at this. The test statistic for testing a claim about a proportion is the z-value. P hat minus P over the square root of P Q over N square root. So that's your test statistic. Now, if you're using computers, technology of some sort, an application, a lot of these will be done for you already. Actually, I get it back. I did find the stat thing that they use in the book. But in order to use it, you have to have the data entered. So I didn't want to enter all of them. So it is in there. It's just that you have to make sure you have it on there. So remember, we have 3 types. We have the p-value. We have the critical value. For both of these, we use standard normal distribution. Those are the tables, the Z chart tables. And the claim. Here's one. Most internet users use two-factor authentication to protect their online data. Okay, this was given to you at the beginning of the Pew Research. It said the chapter problem cited a Pew Research survey of 926 internet users. And 52% of them said yes, they do use a two-person authentication. So we have to make sure we have everything we need from our list earlier. Is this a valid? Is it valid? We have all the information we need, so we can start using our process. So, like it says here, the requirements. The first requirement. Are the subjects randomly selected? Yeah, they're just asked them, so there's no rhyme or reason. So we know n equals 926. Is it okay, is this test a binomial distribution? Why? Because what are the possible answers? Yes or no. So is there a fixed number of responses? Yeah, there's 926 of them. Are the responses binomial in nature? Yes, either yes or no. Are those true? Remember, n is 926. P is 0.05. Why is P 0.05? 50-50, right. So P is 0.5, then Q has to be 0.05. So n times P is greater than 5, so we have 926 times 0.5. So half of 926 is 463, and that's bigger than 5. Same thing with the Q factor. 926, 0.5, is that bigger than 5? 463 is bigger than 5. So yes, those both work. Since the conditions exist, now we can go ahead. You notice this is very important whenever you do any type of statistical analysis. You have to make sure your data is valid before you go any further. Your data, your sample, everything. So let's look at the p-value method. Going to do technology. But which chart are we going to use? Or do we need a chart? Since we know n is equal to 926, we know p hat is 0.52. From our survey. What value do we use to find our critical value? In other words, we're looking for significance level. What are we doing? What do we normally use? Okay, so we know our critical, we're going to use that as our critical value. So the first step, claim. We have to define our null hypothesis and our alternate hypothesis. So what was the claim? Yeah, it's saying most internet. So what's that going to look like mathematically? If it's most, then it's greater than 50%. So is that going to be H1 or HO? Which one does not have an equal sign in it? You sure? H1. So this one says P is greater than the null hypothesis is we're saying either greater or less than or equal to 50%. So we're just gonna look at that. You can go, or if you wanted to, you can say less than or equal to 0.05. So once we know this is the claim, then we find the other one. Will it always be the H1 that's being claimed? Give me an example where H1 would be claimed or HO would be claimed. What if the statement said at least 60% of those surveyed used two-factor authentication. If it said at least, what does that mean? At least means greater than or equal to 60%. So that's HO. So H1 would be less than 60%. So it's not always going to give you one or the other. It's just, it'll give you what it gives you. Step 2. Significance level. Typically, we use 0.05. Now, here's a side note. If you're doing a statistical analysis and you use 0.05 and your answer doesn't come out right, or doesn't support your claim, change your level of confidence. Make it bigger or smaller. And change it until it does, either it gets too weird, or you can go all the way up to 0.1, 10%. And if that doesn't work, then don't go any further. But you don't always, this is just the most typical one that people use. Since we have P, approximate P hat. Why do we need P hat? It's in the formula. For our Z value, for the statistic, we have to have P hat minus P. So we have to calculate what P hat is. So let's see what we have here. And find Z. So do we have N? Yes, that's 926. Do we have P? That's 0.5. Do we have Q? That's 1 minus P, 1 minus 0.5, which is 0.5 also. Do we have P hat? That's what we did up here. I'm sorry. P hat is N times P over N. No, that's another formula. Yeah, it's N times our five two, because it was stated that 0.52, but now we figure out what the value is. Yeah, the p hat value is 0.52, but 0.52 of what? 0.52 of N. So p hat is 926 times 0.52. That equals 482. Calculate Z. Z is equal to P hat minus P over PQ over N. So it's 480. These have to be in decimals, so it's our formula 482 divided by 926 minus 0.5. This is 482 divided by, so let me go to my spreadsheet. Was that? Yeah, it was, it's 0.52 of that, but now in this formula, the p hat, these are actual proportions. Because we can't use 486 here, and that's a 0.5. So it's p hat, the value of as a proportion is the 480, what was that, 482 divided by our N. Because it's 0.52 of 926. That gives us a value. But what is the proportion value? It's a percentage type. So it's this value, which is 482 divided by 4, because that's where this came from. Because we have 926, so 483 of one and 483. This formula would actually look at 4.52 times 926 divided by 926 minus 460. Oh, where is that one? So it's half 926. It's 483 over 926. If you look at, notice all of these, this is p hat. It's 52% of 926 divided by 926. What's that proportion? This one, since it's 50-50, what's half of 496, 926 is 483 divided by 926. So this equals 0.5. This equals 0.52. And these are also proportions, ratios. We plug all those in our formula. We have 82 divided by 926 minus 0.5 divided by square root of 0.5 squared divided by 926. So our z value is approximately 1.25. Why is it 1.25? Because our z chart has two decimal places. Now, do we have a one tail, two tail, or one tail left, one tail right, two tail test? What kind of test do we have? How do we determine what kind of test we have? Why? Right. Let's look at H1, the alternate hypothesis. It's pointing to the right, so our chart is one tail right. Our z value. What's our p value? What's our p value? The p value is the area, that's shaded region, to the right, or to the left. No, our p value is to the right. So we're looking for, this is our p value right here. So how do we find that area? And put one to the right. So we have to go to 1.25. 1.25, which is 8944. So this whole area here is 0.8944. So this area is 1 minus 0.8944, which is 0.1056. So now what do we do? How do we use these two values here? Do we accept or do we reject our null hypothesis? Or do we reject or do we not reject our null hypothesis? You do what? How do you do that? Alpha is 0.05.
Not high enough to say the certainty that more than.
That what you're saying? That's our p-value. Because since our p-value is greater than our confidence level, then we fail to reject it. That was using the p-value method. What if we did the same thing using the critical value method? So pretty much most of the stuff is the same. Most of this stuff is the same. To finding the z value. Everything pretty much else is the same. Because in the p-value, we found z with that formula. The critical value method using alpha and the graph. So we know it's what kind of test. It's a one tail right test. We know alpha is 0.05. So where does alpha go in our chart? Alpha is this, the critical region. And if that's our alpha, then what's this area here? Zero 0.9500. We use this to find the z value. So we look at our chart closest we can to 0.9500. And it's between 1.64 and 1.65. So z is equal to 1.645. What was our test statistic? For this one? What was our test statistic? Because we need to know the test statistic, because if it falls in the critical region, then that determines whether we reject or fail to reject the null hypothesis. It was one, yeah, there it is. 1.25. That, this is our test. So in our example, this Z value was 1.645. Our test value was Z equals 1.25. That falls over here. Does it fall in the critical region? No, since it doesn't fall in the critical region, we fail to reject HO. Then Z equals 1.25. That does not fall within the critical region. In other words, 1.25 is less than 1.645. So pretty much the p-value method and the critical value method are the same things. We'll get the same solution, pretty much the same numbers, because they're based on the same information. However, the third method the confidence interval method. We're using the same information. We have alpha is 0.05 as our significant level. Now, when we deal with confidence interval, what's the difference between confidence interval and the other ones we've done? The confidence interval, you have an interval. Pretty much you have two-tailed test. If this is 0.05, that means this one has to be 0.05. So our alpha is 0.10. So we're looking at what's called a 90% confidence level. So that means we have to find the values here at both ends. Because what we're looking for is this. We have the lower bound is less than our P and our upper bound. That's what we're looking for. That's why it's called the confidence interval. We're 90% sure that our answers are going to fall within these numbers. So we have our N is 926. Our X value is 482. Because of our P hat is 0.52. Was look at your notes for section chapter 7. I don't have those with me here. For the confidence interval. There's a formula for both ends here, or a process. Find both ends here. Remember, it's the confidence, it's the same as the mean plus or minus 2 standard deviations. Look at 7.1. Where'd you get that from? But what's the calculation? From given this information, how do you get it? I don't want the numbers. I want to know how the procedure is important, because in your homework, it's not going to be these numbers. Yeah, and mine are on my other computer. That one that died. It's your chapter 7. What's that? Mm-mm. Well, actually, it will help define it. That's what it is. Margin of error is how far these are apart. What's that? I don't want the value. I want the procedure. And what's E? Yeah, yeah. E equals what page is it on? Yeah, so it's yeah. We won't need that critical value part. 25. Okay, so P hat is 0.52. So it means Q hat is 0.48. N is 926. I hate that thing. Thank you. And alpha is 0.05. So we gotta find the Z value for alpha is 0.05. 0.52, 0.48, 926. So if alpha is 0.05, then alpha over 2 is 0.025. That gives me 0.25, 0.5987. Be that much. I need to find the Z value for that. And 0.5987. Drawing a brain fart. Because we have P hat, that's 0.52. The E, this part's super easy. We just did that. The Z alpha over 2. If alpha is 0.05, over 2 is 0.05. 0.025. We're dealing with two-tailed test. So this is 0.025. This is 0.025. It's on the negative side, 0.025. 0.025 is negative 196. And for this side, it would be 1 minus 0.25, which is 0.9, 0.025. 975. And 975 is 1.96. Your packet is, yeah, your packet you get. Chapter 7. Please, thank you. Now we got the Z values. Well, let's see where that takes us. Thank you, thank you again. So we have wow, that's why this looks wrong. Because this goes in there. So it's 1.96 times the square root of 0.52 times 0.48 divided by 926. So that is our lower bound, 0.033. So our answer is going to be 0.52 minus 0.033, and then 0.52 plus 0.033. Was it 322? Okay, 322. 322. 0. Let me make sure I put that. 0.0322. 0.0322. 0.32. Thank you. So we have 0.52 minus 0.0322, which is 0.4878. And then 0.52 plus 0.0322. So there's my confidence interval. And this is a little bit off because of the values that we're using. We didn't use if you use technology, it'll give you more, I'll say more accurate, present all the decimal places. Because of round off errors, this is what we came up with. If you use technology, you'll come up with something like 494. But zero, this one here, 0.0548 rounds up to 55. So that's pretty close. And this one is pretty far off. And since our p-value, we said is going to be bigger than 0.5, that was our claim. So what's our conclusion? What was our test value? Our test value because we're not in the critical regions, we're inside there. We're inside this. We're inside here. That one falls within there. So we fail to reject HO. Let's do one more example. This don't want to give me a headache. Fewer than 30% of adults sleepwalk. So this is the statement. A study of sleepwalking or nocturnal wandering was described by Neurology magazine and included information that 29.2% of the 19,136 respondents said they sleepwalk. Again, for our example, we're going to use the same confidence level. Our N is 1936. Is it a binomial distribution? Yes, it's either they sleepwalk or they don't sleepwalk. Is it a fixed number? Yes, it's 1936. Does NP, is it greater than 5? Or is NQ greater or equal than 5? P is 30% or 0.3, so Q is 0.7. So 19,136 times 0.3, 19,136 times 0.7, is that greater than 5? Well, yeah, 70% of net is bigger than 5, 30% is big. So those are gonna be good answers. So our claim. Our claim is that fewer than 30%. P is less than 0.3. That's our claim. So our HO is just the opposite. It's either greater than or equal to but because this is a binomial distribution, that's why we just use equal sign. Do they sleepwalk? Yes or no? Although anything that's greater than 30% would work. So we have our null hypothesis and our, so it's a one tail left test because of that. Remember how we found p hat? That was the question you had a while ago. The formula it's our p times n over n. Two parts. 2, 3, 18, 1, 6. We must have to figure out our z value. Yes. No, there's, I have to go to, that's first, I have to first find P. Because I don't know P yet. What's my P value? You would think the P value would be 0.5. Well, yeah. See, now if we had. That would be P.
Well, no.
The P value. That's the P value. Because look at it, because in our formula, if we had, if P is bigger than P hat, then we have a negative value. So would that work in this one? Since it's a one-tailed test, we're supposed to have a negative value.
But P times N over N.
This is just canceled.
I don't think that's a usable equation for this problem.
Not for this one, no, because we want to give it the right information. So,
These were using.
so we have two numbers that we have to deal with. Or, since we're dealing with a one-tail left test, our Z value has to be negative. So because of that, P has to be bigger than P hat. So P hat has to be the smaller one. And P has to be the bigger one.
That was a percent. Right, it's proportion.
Because, yeah, we need to have this to be a negative value. So our Z value is 0.292 minus 0.3 over 0.3, 0.7 over 19,136. And we're using alpha as 0.05. So 0.05 is between two numbers. Let's first find this one. So that one's going to give us, because that's going to give us our critical value. Top we have 0.292 minus 0.3. divided by square root of 0.3 times 0.7 divided by so my z value is negative 2.42, 2.41. So that's my z value. So I go to my chart at negative 2.41, that's 0.008. My z value was negative 2.41, and the area is 0.008. And our value here, 0.008, is less than 0.05. That means it falls in there. Yeah, once you find the z value, once you do that z value, we found the area, the probability. And then now where's our confidence level? Our confidence level is out here. Well, this is our confidence level. And 0.008 falls inside there. Since it falls in there, we reject the null hypothesis. Since our value falls in the critical region. Oh, wow. Sorry about that. I just had a brain fart. I don't know what I was thinking. All right, that does it for that section.